So we are going to do an example problem related to our kinematics, our one-dimensional kinematics to be precise. So I'm going to set up a situation, one that we can solve, hopefully, of a pen rolling off of my desk or my lab table. Okay? We're going to say that the pen rolls off and falls 1 meter. Okay? So the top of my table is 1 meter off of the ground. So we've got a y right here equal to 0, and we've got a y up here equal to 1 meter. Okay? So I'm going to declare a coordinate system, which I kind of already have since I have coordinates listed here. I'm going to start with my y equals 0 down here, and since I go up, like we normally do, up is my plus y direction. Now we're only going to deal in one dimension, so my pen kind of is rolling off the table. Let's say that it starts basically here, and it's just like the tennis ball that we looked at before, where I let go of it, it just drops. So since it's just dropping, our initial velocity, v naught, equals 0 meters per second. Okay? Now my desk is not on the moon or some crazy other location. So we have our regular acceleration in the y direction of negative 9.81 meters per second squared. All right. So we've got a bit of an idea of what we know. So we're kind of jumping ahead. Two main questions we normally ask are, what do we want? That's usually something you get from the problem itself. And in this case, since I'm generating the problem, I'll tell you what I want. Let's find out what our impact velocity is, what our final velocity is. Basically, how fast the pen is going when it hits the ground. That's what we'll start off and look for. Okay. What do we have? Well, looking across our chart at our variables, we have delta x, which in this case is delta y. Do we know our displacement? Actually, let me erase that. I said one thing and then drew the other. Delta y. Do we have that? Well, we know that we start up here at 1 meter and we end down here at 0. And so delta y is the same thing as y final minus y initial, which is going to be, my final is 0 minus my initial, which is 1. All right? So delta y equals negative 1 meters. Turns out we have it. Good. Okay. This is our final velocity, the next one over. That's actually what we want, so that's a good one to keep track of. Our initial velocity, v naught, equals, well, it's falling from just falling off the table there, so it doesn't have any initial y velocity, 0 meters per second. Our time, don't know. And we're not asked about it, so we're going to ignore it. That's our don't want, don't need, don't have. And finally, our acceleration, which we have listed up here in our y direction, is negative 9.81 meters per second squared. Okay, so we've got 1, 2, 3 pieces of information. We want to find a fourth one. We should be in good shape. So we want to find out what we don't want and don't have. Well, like I mentioned, that's our time. So we go to our chart, and we find the one equation that doesn't have time in it. So I look in the time column, I go down, there's no check here. That means this guy right here, equation number 4, down our list, is the one we want to use, because it doesn't have time in it. So we've got v final squared equals v initial squared, plus 2 times the acceleration times delta y in this case, because we're dealing with a problem in the y direction. Okay. Well, this is pretty good, because we wanted to solve for our final velocity anyway. All we have to do is take the square root of both sides. Pardon me. We'll have our final velocity equals the square root of our initial velocity squared plus 2 times our acceleration times our displacement in the y. Okay, so let's start plugging in numbers. Our final velocity equals the square root of 0 squared, which is a whole lot of 0, plus 2 times negative 9.81 meters per second squared, times delta y, which equaled -1 meters. Okay? We take the square root of all of that. Okay, so v1, our final velocity, is the square root of, I'm going to grab my calculator, 2 times -9.81 times -1. And those two negatives cancel each other out and we get a positive, which is good because if we had a negative under a square root, we'd be having a bad day. We get 19.62. All right, so we take the square root of that to finish things up, and we end up with 4.43 meters per second. Okay, because we had meters per second squared times meters, so we end up with meters squared per second squared. But then we take the square root of it, so it gets rid of those squares, and we're just left with meters per second. So our units work out, which is great. Now there's one small thing that we don't want to lose track of in this. It's a little tricky. And the tricky part is, we found v1, it's the square root of this. Well, it turns out, just like all square roots, there are two answers. It could be positive or negative. Because if I have positive 4.43 squared, it gives me 19.62. If I have negative 4.43 squared, it also gives me 19.62. So which do we want? Only one of them can be the correct answer. So let's stop and think. If I have a pen that's falling and it hits the ground, which way is its velocity pointed? Well, it should be pointed downwards because it's falling down. So if the velocity is pointed down, that means we need a negative. So our end solution on this, v final, equals negative 43 meters per second. Put a square around that. That is our answer. Okay, so for our own edification, let's find out what the time was. Just because I like to get the most out of problems that I work on. Well now, since we know everything except for time, we could use any of the equations that we wanted. However, let's go ahead and assume that, hey, maybe we made a mistake on our final velocity. So let's use the one equation that doesn't rely on that final velocity so that we're certain that we've got a reliable answer. On your chart, that'll be the second one down, which is one of our more popular ones. Delta x equals our initial velocity times time plus 1/2 at squared. Now, if we had an initial velocity, this guy could quickly become an unpleasant quadratic. At which point I would say, let's trust this value and see what we get from that. But luckily, our initial velocity is equal to 0, so that's going to make this term disappear. But let's see what we get. All right, so going through the best way, oops, not delta x, delta y. All right, so we know our delta y, it was -1 meters equals 0 times time plus 1/2 -9.81 meters per second squared times time squared. That whole thing goes to 0. Let's see. So we'll have -1 meters equals 1/2 -9.81 meters per second squared times time squared. Okay, so if I get time by itself, I'm going to multiply by 2 on both sides of my equation, so I don't change anything. I'm going to divide by -9.81 meters per second squared. Okay, so if I evaluate this, I end up that, well, this is just t squared, 0.204. So I'm going to take the square root of both sides. I end up with 0.45 equals t. It's 452 actually if I round it appropriately, but 0.45 will be good enough. Okay, so we found our time. Now, one of the things to keep in mind is on a different problem, if our initial velocity wasn't 0, then this probably would have become a very unpleasant quadratic, at which point we could have simply taken our final velocity and used a much prettier equation, like maybe equation number 1, and that would make it much easier. So as an overview, we started out, we drew our problem, we set up our coordinate system so that we had a good idea of where the motion was happening and we could get our values. Then we asked ourselves our two questions: what do we want? What do we have? We filled that in. And then, after we identified that, we used that information to choose which of the kinematic equations we wanted to use by finding out what we didn't have and what we don't want. And then we use the equation that doesn't have that. We solve that equation for our value, and we end up with our impact velocity, which is what we were looking for. And with that information, we can move on and find any of the other values that we want. So that was this particular sample problem.